Welcome back to the Deep Dive, where we crack open the most complex technologies and give you the blueprint. Today, we are strapping on our hard hats and going straight into the engine room of modern generative AI. We're not talking about training data or marketing. We're targeting what makes these massive transformer models like Meta's Llama 4 run so efficiently.
That's exactly right. I mean, when you look at the scale of these LLMs, we're talking billions of parameters, context windows, and the thousands of tokens. The whole operation hinges on the attention mechanism.
Right.
But the math you learn on paper, that's only half the story. The real secret is in the execution of that math.
And our mission today is laser-focused on that execution. We are dissecting scale.product-attention SDPA, specifically that highly optimized PyTorch function, torch.nn.functional.scale.product-attention. This is basically the single line of code that shortcuts years of computational engineering.
It is, and we're going to understand what it does and, crucially, how it gets its speed. We've pulled together the official PyTorch docs, we've analyzed the Llama 4 code from Meta's GitHub, and looked at some technical commentary to really zoom in.
Okay, so let's start with the core problem SDPA is built to solve. Attention, historically, was this huge computational bottleneck. Why was it such a massive drain?
Well, the curse is scale. Specifically squared scale.
Squared scale.
In the original transformer, the attention mechanism had to compare every single token in a sequence with every other token. So if you have n tokens, that's n squared comparisons.
Okay, which gets big fast.
It gets big very fast. But the computation time is one thing. The truly painful part was the memory bottleneck.
The memory bottleneck. Explain that for us.
So when you do the core attention steps, calculating scores, masking, Softmax, you create these huge intermediate tensors. That main one, the Softmax matrix holding all the weights, is n by n in size.
Right.
So if your sequence length, n, goes from, say, 512 to 8,000 tokens, that matrix gets 256 times larger. And standard implementations had to read and write that entire n-squared matrix back and forth to high bandwidth memory, or HBM. That's the main kind of slower memory on your GPU. That movement is the absolute killer.
So even if the math is fundamentally O(n) squared in time, the big optimization isn't about the math, it's about making the memory usage manageable.
Precisely. That's the whole game. SDPA, especially with modern kernels, lets the model weigh the importance of different inputs without totally drowning the hardware in memory writes.
Okay, so let's unpack this optimization. Why is this specific PyTorch function so much better than me just, writing out those 6 attention steps myself?
Because it's an abstraction of hardware intelligence. When you call this function, you're not just executing math, you're running an intelligent wrapper.
An intelligent wrapper?
Yeah, it was introduced in PyTorch 2.0, and it's designed to automatically pick the absolute fastest backend available for your specific hardware.
That's fascinating. It's like a smart router for your computation.
It is. And on NVIDIA hardware, where almost all of these models run, it strongly prefers to use these highly specialized fused kernels. The big one is FlashAttention.
Okay, we have to dive into FlashAttention. That's the real secret sauce, right? The O(n) memory scaling everyone talks about. How does it cheat that O(n) squared memory rule?
It's a genius use of the memory hierarchy. Let me give you an analogy.
Please.
Imagine your total sequence n is a giant filing cabinet. That's your slow HBM. To do attention, you create this massive scratch pad, that n-squared Softmax matrix. Normally, you have to keep writing that scratch pad back to the filing cabinet. It's slow, and it takes up a ton of space.
And the scratch pad just explodes in size as n grows.
Exactly. So FlashAttention uses a technique called tiling and kernel fusion. Instead of doing the whole sequence at once, it breaks the query, key, and value tensors into smaller blocks or tiles.
Okay.
It brings those little chunks into the GPU's incredibly fast on-chip memory. The SRAM.
Yeah.
Think of SRAM as your small personal desk.
So the SRAM desk is fast but small.
Right. It then does the whole attention calculation for just those tiles right there on the desk, all 6 steps. And it never, ever writes that huge intermediate matrix back out to the slow filing cabinet.
So it completely bypasses the memory bottleneck.
Completely. By keeping the intermediate stuff local, it effectively scales memory usage down to O(n). And for a model like Llama 4 with its huge context windows, this is, it's non-negotiable.
That makes the importance of this function so much clearer. It's not just faster math, it's smarter memory management.
That's it.
All right, let's look at the function's blueprint, the signature. We need query, key, and value tensors. What kind of shapes are we talking about here?
Right, so we're usually in a multi-head environment. The tensors need to handle batch size, number of heads, sequence length, and the embedding dimension.
Okay.
So the query, or Q, is what we're looking for. It usually has a shape like N, H, Q, L, E. N is batch size, L is the query sequence length, E is the embedded dimension.
And we compare that against the key and value, which is all the stuff available in the context.
Yep. The key, K, and value, V tensors, they both have the source sequence length, S. So their shape is something like N, H, S, E. And, sometimes the number of query heads and key value heads can be different, which is something this function can handle.
That sets up the basic structure. But the optional parameters are where the real control is. Let's start with masking.
The mask parameter is, it's for spatial control. It tells the model where not to look.
Like for padding.
Exactly. If you batch sequences of different lengths, you use padding tokens to make them all the same size. The mask stops the model from paying attention to that meaningless padding.
But then there's this gazelle, which seems absolutely critical for a text generation model like Llama.
Oh, it's vital for any autoregressive model. Setting scazzle true automatically applies a lower triangular mask. Think of it like a filter. When the model is generating token 5, it can only see tokens 1 through 4. It can't peek ahead at token 6. That would be cheating.
So scazzle true is what makes sure the text flows chronologically.
Correct. And it's important to know you can't use a custom @mask when iscazzle is true. The causal mask is already doing all the heavy lifting for the context window.
Let's move to the scaling factor, the scale parameter. If you leave it unset, it defaults to 1 over the square root of E, the embedding dimension. Why do we have to scale the scores?
This goes back to some high-dimensional math. When you calculate the dot product of two really high-dimensional vectors, the scores can get massive.
Okay.
And if those raw scores are too big, when they go into the Softmax function, you can get a really bad problem called saturation.
Saturation?
Yeah.
I thought Softmax was good at handling large numbers.
It is, but if the scores are gigantic, Softmax will push the probabilities to be extremely close to 0 and 1.
Yeah.
And when you have probabilities like 0.99999 and 0.00001, the gradient of your loss function becomes almost flat. So during training, the model just stops learning. The gradient vanishes.
The classic vanishing gradient problem. So scaling just pulls those scores back into a stable range before they hit softmax.
Exactly. It keeps the probabilities distributed enough that the model can actually learn from them during backpropagation.
We also noticed an experimental parameter, an EBLECA, grouped query attention. Why is that an efficiency function?
GQA is another resource saver, mostly for speding up inference. In normal multi-head attention, every query head gets its own unique key and value heads.
Right.
GQA just says, hey, we probably don't need that many unique key value heads.
So it cuts down on redundancy.
Yes. You might have, say, 32 query heads, but only 4 key and value heads. GQA just reuses those 4 KV computations across all 32 query heads. It massively cuts down on the memory and compute needed for the key and value projection.
Which gives you a huge speed up, especially for inference.
A huge speed up.
Okay, that covers the parameters.
Mm-hmm.
But you said the real power is fusion. Let's go inside the black box. What are the 6 steps this function fuses together?
Right. These are the core math operations. But just remember, they all happen in one fluid kernel operation.
Okay, step 1, measuring similarity.
Dot product scores. You compute the raw logits. Scores equals query at key dot transpose. This matrix multiplication just tells us how much every token in the query relates to every token in the key.
Step 2, stabilization.
And scaling. We take those raw scores and multiply them by the scale factor. That's the step that prevents the saturation we just talked about.
Step 3 manages the context window.
Masking. Here's where the function applies either the padding mask or that automatic causal mask. It sets the scores for any forbidden positions to, effectively, -infinity, so they get 0 weight in the next step.
And step 4, turning scores into actual weights.
Softmax. The normalization step. The scaled and masked scores become at-weights probabilities that sum to 1. This tells the model exactly how much importance to place on each token it just looked at.
Step 5 is mostly for training, right?
Dropout. Yep. During training, you can randomly zero out some of those attention weights. It's just a regularization trick to stop the model from getting too reliant on specific connections.
And finally, step 6, putting it all together.
The weighted sum. The model multiplies those normalized atom weights by the value tensor, output at where weights at value. This aggregated result is the final attended output, a new representation of the token that has all the relevant context baked in.
It's just astounding that all 6 of those steps can be fused into a single call. If I tried to write that out manually in PyTorch, what kind of slowdown are we talking about?
Oh, orders of magnitude. You do step 1, write the result to HPM, Load it for step 2, write it back. Load it for step 3.
I see.
All those read-write cycles are what kills you. Fusion means all 6 steps happen on that fast, local SRAM disk. You only write the final output back to the slow memory at the very end.
So the breakthrough really isn't the math, it's the memory management. Okay, let's jump from theory to reality. How does Meta actually use this inside Llama 4? We've got the quote snippet here.
It's the centerpiece of the self-attention layer in the transformer decoder blocks, and since Llama 4 is all about handling long dependencies, this function is absolutely critical.
Let's break down the main line. At output, fscale.product tension. XQ, XK, XK, or EFV, at mask masking dropout P0.0.
So XQ, XK, and FishV are the projected query, key, and value tensors. These aren't the raw embeddings. They've already gone through linear projection layers, and, really importantly for Llama, they've incorporated rotary positional embeddings, ROPE.
ROPE, that's Llama's way of injecting positional info, right? So by the time Q, K, and V hit this function, they are fully context-aware.
Exactly. And we see at Miraskip, for Llama, this is probably a combined mask that handles both the causal restriction and any padding.
And dropout P0.0 is hard-coded. Does that just mean it's running in inference mode?
For a production model, yes. Dropout is only used during training to help with generalization. When you're serving predictions, you want deterministic results, so you turn it off.
Okay, the function returns at and output. But the snippet shows there's still some reshaping to do. Why the post-processing?
Well, the attention operation splits the processing across all the different heads. To pass the result on, you have to gather all that information back into one single hidden state.
So what's happening there?
First, you see transpose, 1, 2. That swaps the sequence and head dimensions. It's just getting things in the right order to be consolidated.
Then there's contiguous.view,
Right.
BSC, Sequelin, Nakinda1. I always see that contiguous call. What's it actually doing?
It's a memory thing. A transpose operation changes the tensor's metadata, but it doesn't always physically reorder the data in GPU memory.
Yeah.
If the data isn't physically contiguous, the GPU has to jump all over memory to grab the data for the next operation, which is super inefficient. Contiguous forces the memory to align so the GPU can just stream it efficiently.
That's a great tip. And finally, the view just reshapes it back to the full hidden size.
And that output then hits the final linear layer. Output self.wo at an output. The self.wo or wait out layer just mixes the outputs from all the heads back together into one coherent representation for the next layer of the transformer.
So the big takeaway here is that Meta relies on this one PyTorch function because it bundles all this incredible optimization, flash attention, GQA, memory checks into one reliable call.
That's the entire story. We started by saying attention is the bottleneck. Well, fscale.product tension is the foundational mechanism that breaks that bottleneck using these fused kernels. It handles the scaling, the masking, and that radical memory boost from ON squared down to ON.
So we've learned the 6 steps of attention and the key parameters, but the real performance of every modern LLM lies in the fusion and the hardware-specific tricks sealed inside this one elegant function.
Right. And that raises a really interesting question for you, the learner, to think about. We've engineered solutions like flash attention that drastically cut down the memory bottleneck, but the computational time cost is still, at its heart, ON squared. So how much faster can these attention mechanisms really become before the fundamental quadratic complexity of the computation itself becomes the final unavoidable wall?
A great thought to chew on as these models just keep getting bigger. That's all the time we have for this deep dive into the Transformer engine room. Thank you for joining us.